Um, in this chapter, we will start uh, studying optimization problem like min and max of a function of several variable over a set, particular set. This set this time S is described by the set of X in Rn, okay, such that g of X is equal a constant, okay. So this relation where g can be a vectorial function g1 gm, okay, with m less than n, the dimension, and c is a constant vector c1 cm, okay, belonging to Rm. So the difference here, the set we have here now, it can be with an interior that is it is with an empty interior. So it's different from the first category of non-contained sets. For example, if I have a function of, for example, G could be an example to concretize. If I have x, y, z and consider x2 plus y2 plus z2 equal 1. Yes, so here and the dimension n equal 3 and m equal 1. It's clear that the interior of the set is empty. My set is just the unit sphere. You see, it's the unit sphere. And so yes, now looking for a minimum maximum of a function over this set, the only tool I have is to check the definition. I will say that an x star is a solution, is let's say a minimum or maximum. So let's say yes, it's a maximum, is a maximum point, max if and only if we can check that fx is less than fx star, okay, for any x in the set S. See, this is also for global. This is for global, relatively global extreme point, okay. Local also, we can relatively local, okay. We need to check this locally on this surface. So usually what we did for when we were working in a ball, we were able this is for global. For relatively local max, we will say we will need to check fx less than fx star, okay, for any x, let's say a ball centered at x star with a reduced intersection with my set S. Okay, so I can imagine I have something. So here it becomes more complex to understand, to explain what is happening here. So I have something, a sphere. Okay, now if I have my x star, let's say, depending on my function how it is, if I say this point will at this point I will have local maximum. So if you take the intersection with a small ball center, that is, maybe we will get something, let's say part of this surface, okay. We will need to check this comparison on this set just locally, okay. So when we were working with a set S, with non-empty interior, we were comparing. We were able to compare locally on a ball, a filled ball. So we were able to move along. So compared. So this is part of G. So let's say this is the set G equals a constant equal 1. Okay, this is for, yes, when I was working like that. But when we were working differently on a different set S, so we were comparing locally what is happening. Okay, so yes, so we were able to consider points close to x star, close to x star, but close in different directions. Okay, we were working like that. X star is here, so I was considering a ball completely, and I could move, compare for any x, no restriction. Okay, as long as I am inside the ball BR at x star. But this time, no, I have this part, let's say is BR at x star intersect with S with G equal 1. Okay, okay, so here I could point on in the ball can be expressed. I could compare like x star plus H, okay, less than fx star, okay, with H belonging, so with small h, with norm of H less than, let's say, R, okay, a vector. But here I can't do that. I can't. If I do this comparison like that, I will leave my set. Okay, I will. I cannot remain in my set. So this is causing problems. So how can I make? How can I make this comparison? So the purpose. What is our purpose? Why we are asking those questions? Because we have a purpose that. Our purpose is to find, okay, find necessary condition, practical ones, necessary conditions, okay, for local candidates, okay, local candidates when we are working on sets like this one, okay. So this is because it's not practical to use just the definition where to find those points, okay. So now the problem, the next, the others, the problem we are seeing is also how we can move along this set, remaining close to x star and remaining on this surface. For example, in this case, it is a surface. We could be moving along a curve. How we can express this? They can find what is the tool that can be used so that it allows us to make this comparison. So the idea of the tool is to consider curves passing through the point x star, okay, and compare, and we can imagine any curve, any regular curve passing, okay. So those curves that are xt, okay, with t belonging to, let's say, minus AE, because it's local, we want them going part crossing the point x star, and you have points from both sides of the curve, and x at 0 is x star. So we want regular curve, and x is C1, let's say. Okay, so why not suppose that we consider all these curves, okay, for small, okay, here small interval, okay, as long as we have this. So then look what we can do. We can say that as long as I am on this curve, I can have fx star, which is good. You see, for any t, we make this comparison, okay, and then if we look, and this we said it's our f, let's let's erase this part, and we know that fx star is f at so at x0, okay. This is for any t at from minus a to a. But then if you call this function ht as a composite of f and x, and this one, then this quantity is h0. Then we have one variable function that satisfies, that express this inequality when you have ht less than h0 for any t in a centered interval, that is 0. Then okay, this is equivalent to say 0 is a local max, but then a characterization, then necessarily h prime at 0 equals 0. But what is h prime of t? H prime of t at t equals 0, the derivative is chain rule. We use the chain rule. So here we have chain rule for for function of several variables, so it's the gradient. It's still, we can write it like that, but just x prime of t, okay? I take it at t equals 0. So the derivative here, so it's the gradient of function f, yes, at x0 times x prime at 0. Okay, okay, and we want then, yes, this is equal 0. This is what we showed. That means if we have a candidate point for optimality, maximality, for example, local maximality, necessarily it will satisfy this equality. But still something I need, it mustn't depend on x, on this function x. I want it for any curve like that, belonging to the set of curve xt, that satisfies all these characteristics. Okay, these properties. Okay, so what is, so the idea, if we can identify this set in some way and without introducing these curves xt, it will be, we will get then a necessary condition. You see, yes, a necessary condition that will help us to conclude. That's why we need to study then for the set of constraints. Yes, for a given set of constraints, there's vector. What family, that vectors are describing what for a given content set, like that. Okay, we want to characterize this set. This set is called the tangent plane. Okay, and this is, yes, the purpose of the study here is tangent plane for constrained, for the set of constraints. So tangent plane. So let's define it. So here, so I will give the definition. We will set the definition here. We denote M as the set of all those vector tangents, okay, where xt is a regular curve, okay, C1 curve, x differentiable, include, okay, x prime differentiable, okay, C1 at minus AE, okay, like that, even including A, okay, and what else, x0 equal x star, and xt belongs to S, to our S. So S here is the set where g of x is equal to a constant c. Okay, our function g is a regular function. Okay, so this is the definition. This is what we want. All those tangent vectors, what they are, can we characterize them? We have a characterization given by the following theorem. Here it is. The theorem says under a certain condition, when we have x star irregular, if we have x star is a regular point, what does it mean? That means the rank of the rank, rank of, you take the g prime, the derivative of the function g at x star, and you found it equal m. Okay, m is give us the number of equations. Okay, if it is exactly m, then we say that x star is regular. And then if in this condition the set m is exactly identified to the subspace, the set of all vectors, okay, such that the derivative, okay, y equals 0. So it is a subspace of Rn. Okay, they form the tangent vectors. We call them also tangent vectors. Okay, tangent vectors. Okay, they form this subspace. Okay, and we denote T at x star the set of the translated M, which is the set of all x in Rn that are g prime of x star, so x minus x star equal the 0 vector. Okay, so this is how we can characterize this set. So we will in our study of optimization problems under equality constraints like that, okay, we will be interested in dealing with set constraint sets where there is we have regular points. Okay, so where we have a tangent plane. Okay, tangent plane at this point. Okay, if we consider all the directions of these curves, they form so a tangent plane. Okay, these points we know how. Then we will see the characterization that we started here. We will see how we can obtain a necessary condition. So the important sets we are interested in are this one, where we are able to find tangent plane. So now let's just take some so the proof of this theorem is very it uses the inverse theorem. So it's an you can read it if you want. The proof, it's more heavy to write it than the complexity, because the difficulty comes from the theorem itself, inverse theorem. But if we have it, we can show this. Okay, so let's do some examples. For example, let's continue with the example we started here. So with our G, what will be the at 001? Let's consider the example at 001, 010. Okay, let's take x star 010 and find the tangent plane at this point for the content gxyz equal x2 plus y2 plus z2 equal 1. Okay, so it is clear that g at x star is equal 1. It's part of the curve. It's a point of the curve. Now, what is? Let's check if it is a regular point. So let's compute the derivative. Okay, yz. So it is the vector 2x, 2y, 2z gradient. So the rank. It is clear that we cannot have this vector is different from the zero vector because 0 is not part of the curve, the surface. So the rank here, the rank of g prime is always any point on the sphere is 1 for any x, y, z belonging to the set g equal 1. In particular, at the rank of g prime at x star. Okay, the capital here to make the difference with small x is 1. So x star is regular, is a regular point. So let's see what is the tangent plane, how does it look like. Okay, so the tangent plane Let's continue here. So we said T of at x star will be the set of all, so here x, y, z, such that the derivative g prime at x star, so x minus 0, y minus 1, and z minus 0 equal to 0. So this is, now what is g prime, the derivative? So I'm looking for all the points x, y, z, such that g prime here, the derivative, the gradient, so it will be at 0, 1, 0, so it will be 0, 1, and 0. Okay, dot scalar y minus 1 and z minus 0, you see, equals 0. So it gives us finally y equal 1. So it's the set of all the points x, y, z such that y equal 1. Okay, so let's see, have a look. This is an equation of plane horizontal. It's the vertical plane. Okay, vertical plane. Okay, if you want to, if we want to graph it here, so look at what we can obtain, what we have. So look what we have here. So we have a sphere. The point 0, 1, 0 is here. This is my point 0, 1, 0, and I have a sphere. Okay, so let's, this is my sphere. I have this, the other part. Now, this tangent plane at this point, my point is here, x star, and the equation of my tangent plane is the vertical parallel plane, like that. We have it like that. Okay, so this is the plane y equal 1. Okay, so here I have the curve x, y, and z. Okay, you see, it is the meaning of tangent plane we usually have. Okay, so yes, so this is what the importance of introducing the tangent plane, because we need them later for characterizing candidate point for optimization problem with equality conference.